Hello everyone. In this video, I will explain another method of demodulation of double sideband suppressed carrier signal by using what is called as a Costas receiver. Now, in the coherent demodulation process, this is also a coherent demodulation process, first of all. But in the simple coherent demodulator, where we use some one product modulator and low pass filter with a locally generated carrier, what happens is, if the phase difference between the local carrier and the transmitter carrier is 90 degree, we get something called as quadrature null effect. Now, to overcome this problem, some modification, some kind of feedback is actually used in this method called as a Costas receiver. Now, without wasting much time, let us go to the block diagram of this. Now, just look at this block diagram. This is a Costas receiver, but basically it is a coherent detection only. That means we have to generate a local carrier, which is this carrier cos 2 pi fct plus phi, which is given by a VCO, a voltage controlled oscillator. Okay, but here what is the difference is between this and simple coherent demodulator is we are actually having two coherent demodulators. The one is the top one, the other one is the bottom one. Okay, so this is the one coherent demodulator, this is another coherent detector. So for which both the for which the local carrier is actually applied. The one is applied directly over here like cos 2 pi fct plus phi. For the second case, we are applying through a minus 90 degree phase shifter. That means here the carrier signal applied is sine 2 pi fct, that is sine, let me write the equation here, sine of 2 pi fct plus phi, because cos and sine signal are 90 degree out of phase or quadrature in phase. It is 2 sine 2 pi fct plus this phase difference between the local carrier and the transmitter carrier. So these two signals are applied to the product modulator, and here I am using this VCO and the phase discriminator for handling that phase variation or to compensate the phase variation, for which the outputs are the input for this phase discriminator are the outputs of two coherent demodulators. One is this signal, the other one is this signal. Okay. Now, since we are applying the carrier signal which are in phase quadrature, I call this channel as I channel, the in phase channel, and this channel as the Q channel or quadrature channel. Now, how exactly we produce the message signal here? So the output of the top I channel gives you the original message signal. Here we get the equation as AC by 2 cos phi m of t. In the bottom channel, that is Q channel, we get AC by 2 sin phi m of t. So how to get those equations, I will explain with the derivation now. Now just look at this. So we have a message signal, sorry, the modulated signal, that is S of t, which is given by AC cos 2 pi fct plus phi. So this signal is common for both the product modulators. For the top, the modulator, the carrier signal given is cos 2 pi fct plus phi. The output of the product modulator is given by S of t into C1 of t. Just substitute this S of t and C1 of t. I'll get this particular equation, right? So this equation I will get where this is S of t and this one is C1 of t cos 2 pi fct plus phi. Now apply a cos A cos B rule. I'll get this component and this component, that is half of cos of A plus B cos of plus cos of A minus B. So when you apply that particular rule, I'll get first term as this, which is the actual signal, and this is the other signal. So when these components are V1 of t is given to the low pass filter, only first term is allowed and we get VO1, that is AC by 2 cos of phi m of t, where this part is the amplitude part and this is the message signal which is recovered after passing through the low pass filter. This is the high frequency component which has the frequency equal to 2fc. So this 2fc, or you can say the m of t is shifted by 2fc, we will not be allowed by the low pass filter. So we get this particular component, a scaled version of the message signal. That's what I'll get in the I channel. Now going to the bottom part, that is this part here now. Okay, how exactly we get AC by 2 sin phi m of t, that I will explain now. Let's just look at this. Now the 90 degree phase shifter output is given by sine 2 pi fct plus phi. That's what I told earlier, right? The output of the product modulator is given by V2 of t is given by S of t, the same DSP-SC signal multiplied by the C2 of t. Okay. Now again substituting both S of t and C2 of t, I'll get like this. cos A and sin B rule I will apply. So I'll get this particular term, the first term, which is given by half of sin of A plus B and sin of A minus B, right? This is the second part, which is a high frequency component. This is the low frequency component. When I pass this V2 of t through a low pass filter, I will get this only the low frequency component, which is the message signal. Okay, so difference between the I channel and Q channel is they are having a 90-degree phase difference here. That's it. That's why they are called I channel and quadrature channel. Now, so how exactly? Now I'll go back to the block diagram. How exactly the phase variation is compensated? Okay. Now just consider the ideal case. In the ideal case, the phi is equal to 0, right? That is the phase difference between original carrier and the locally generated carrier, which is given by the voltage controlled oscillator, will be 0. Okay, so in that case, the bottom channel output will be 0 because sine of 0 is 0. So everything will be 0. So in the ideal case, Q channel will be producing a 0 output and cos of 0 is 1. So it will produce the highest amplitude over here. This is the ideal condition. So for this particular ideal condition, okay, when both are given to the phase discriminator, it will say phase discriminator is nothing but it actually discriminates or it compares the phase of the two inputs, the I channel output and the Q channel output, and based on the phase variation, it will produce certain voltage over here. Okay, the function of the VCO is depending on the input voltage, it will produce a oscillation. Oscillation means it produces the signal, carrier signal with a certain frequency and the phase which depends on the input voltage, and this input voltage depends on the phase variation between or phase and frequency variation between the two inputs of the phase discriminator. Now ideal case, it will produce certain amplitude. Okay, let us say some amplitude, say some 5 volt, let us say. Okay, and based on that it will produce cos 2 pi FCT, a carrier without any phase variation, that is 0 degree, let us say. Okay, now let us consider that there is a small phase variation of say some 10 degree, maybe 20 degree or whatever. So during that time what happens is sine of 10 and sine of 10 and just give me a second, I'll go back to the block diagram. Yeah, so sine of say 10 or sine of 20 or whatever, so we will have certain value of sine of something, right? Sine of angle, correct? That means this will not be 0 degree now. During that time, what happens is this will produce a certain amplitude and this also produces certain amplitude. Cos of small angle is nearly equal to 1, right? So we can say some certain maximum amplitude will produce, but both channels will produce certain amplitude, and based on that, that means based on the phase difference, the phase discriminator will produce some other voltage, maybe plus 6 volt, maybe 4 volt or whatever. Based on that, VCO will change its frequency and phase. Okay, and this process, this feedback, this is the feedback, this is the kind of a feedback. This process will continue until the Q channel output becomes 0. Okay, once the Q channel output becomes 0, it will set to a particular frequency and the phase variation. That means now both are synchronized. Okay, now based on the phase, leading or lagging between the transmitter carrier and the receiver carrier, the receiver carrier, this local carrier phase may lead by certain degree or lag by certain degree when compared to the transmitter carrier. Based on that, okay, what happens is the angle will be either plus or minus something. So for a positive phase variation or a negative phase variation, the voltage produced will be different, and based on that and based on the feedback here, it will adjust the frequency and the phase of the voltage controlled oscillator, and hence you can say that the variation, the phase variation is controlled. So the same concepts, same thing I have explained over here by using these lines. Okay, the polarity, okay, the polarity will be different for different direction, the polarity will be same for same direction. Okay, so this is about the Costas receiver, which is used to demodulate the DSB SSC signal as well as to control any phase variation. Thank you for watching this video.